The last one I'll extremely quickly discuss is shape formation. Now, the problem of shape formation is actually interesting. So, I get a lot of visitors in the lab and I want them to be entertained with budgetary swarm robots. So, currently consider with reasonable robots, not budgetary. So, I want them to write down my name, or I want to make them write down robotics with equal font size, which I couldn't maintain. So what you do is you place robots at all the corners and tails, but then there are also places where you got curvatures like this, and that's no corner. So you actually find out characteristic places, equally divide them. Here it's basically the curvature is largest, and then here again it's largest. This is linear. So any object, if you only know the corners, you can still visualize it up, and that's what all the object recognition libraries do. Even humans can do that, only based on corners. If you have extra robots, then of course you can place them up at the other places. The more the merrier. So let me place it one interchangeably at places where the distance was too large. And now what while in a centralized architecture, small number of robots, all the robots share all the information with one system, so everything is known. What would you would do is that, and these are nice big robots, so what you would do is you'll first say that okay, these robots are assigned to R, these robots are assigned to O, and so on and so forth. And with every letter, you'll make it an energy function. So that's a difference to the initial configuration, the current configuration of the robots, and the desired configuration. And the robots move so as to minimize the energy, and the energy is minimum when they take the shape. So they move as a derivative of the energy. That's exactly what is potential field. The derivative of the potential is where the robots move. But then we are not centralized. We are completely decentralized, and the number of robots are in thousands, not just this 10 and 15. So I'll write down robotics like this, and similarly with the others. So imagine first this thing has a bright light. So that's what happens when in events people write down big robotics with bright light, all the LED bulbs and all. So all the insects come and gather here. That's exactly what swarm robots. So all the robots will come here and gather around over here. A problem that you will have is that, let's take two of them. So the density of the robots can be very different. It's local algorithm. So, and therefore you add randomization. Otherwise, the robots in high density here will never go here. So with some probability, they actually go around over here. Bright light will look bad. You need the robots to be visible. Any transmitter emitter pair will do. So any transmitter over here that, and any receiver over here that the robots can detect this shape, that'll do. Of course, the caveat is still that it's not uncontrolled, so you will somehow have to make some attraction possible between the letters and the robots. So there has to be some mechanisms when you've got tens and tens of thousands of robots, which otherwise do not know their position, they don't know a lot of global information, they don't have an access to a lot of centralized data, and so on and so forth. So the only way is that the characters attract. There's a related problem. So I talked about this delitting, taking the litter and just transporting it up. There's a related problem. This time I've got a bigger litter. So it's a pack. and therefore it's heavy. One robot cannot pick it up. So actually you've got swarm of robots that you want them to be distributed all the way around over here. And the problem is called as the collective transport. So again, you want the robots to, all around the litter, you want them to be attractive, and the robot should feel that attraction and should come over here. The equal distribution at the periphery is exactly the same as the equal distribution at the periphery over here, and that will actually happen because all the robots repel each other. They're at such a small distance that only repulsion is going to be active. In any case, there's no attraction there at the largest attraction. So when there's only repulsion, they'll obviously disperse. So this is a normal dispersion behavior. So if you consider this robot which is not dispersed over here first, so what does it feel is it feels attraction over here and it feels repulsion from this robot over here. It doesn't feel the repulsion because it's too good. So it goes somewhere around over here, but now it feels attraction over here. So it again comes here. And similarly, if you take the example over here, so let's keep too many robots over here. So eventually what happens is this feels repulsion from all them, and that's why it goes over here. This feels repulsion from all this and it intends to go out, but then it also feels attraction from this and gets in by the time all these would have dispersed. So dispersion takes care of them being distributed. Caveat, you will have to add randomization, otherwise there will be local minima where the robots will get stuck. After that, they all have clippers, and because they all have clippers, they attach the clippers. And we assume that the litter is something that you can clip it. Take a needle, just press it. And once the clippers get attached, then it is just a collective motion. So collective transport, it basically goes in stage one, which is this dispersion. Clipping is automatic, and then it follows with a collective motion. So that was all that we had from a swarm robotics behavior. It's actually one of the interesting fields because at one time people said that the robots are so expensive and there's so little that you can do. Don't believe on all the videos that people show you, big companies show you. Many of them are choreographed. So people buy such ridiculously expensive robots. There's so little that they can do. And therefore, could we have exactly the same philosophy as in randoms, as in natural swarms, that I have chocolates at home, all my human intelligence cannot find it, and I'm an expensive human being, I charge a lot for taking the course, but hundreds and thousands of ants can find it. So instead of buying one expensive robot, can I get a better performance? Can I get a better functionality? Can I get a more functional, more flexible functionality? Can I get a more reusability? Can I get more adaptivity? Can I get a better overall return on investment instead of spending lakhs and lakhs and lakhs and lakhs of rupees or crores of rupees on one expensive robot? Can I buy tens and thousands of robots? And that's also what you would love. In a very flexible way, you buy 100 robots, which will cost you just 10, 20,000, affordable. And then they do something. Then you're like, okay, these robots are doing good. Let me invest on more robots. Then you buy another 500 robots and they do better. Then you're like, okay, I'm getting my job done. These are very good. Then you buy more robots and then they do it even better. So it's completely as per your job, as per your market needs. And once your job is done, you don't no longer need robots. Then you say that, okay, I sell it to other people, and there are 100 people. And unlike one expensive robots, which will have sensors specific to the person's needs. Here you can just say, okay, you take 20 robots, give me my money back. You take 500 robots, give me my money back. You take 700 robots, give me money back. Such a beautiful picture. So a lot of emphasis was that can multiple robots, which are too many but still don't have a high cost because each one of them is a budgetary robot, outperform a single expensive robot, and in a way such that your investments are timely and your returns also keep on increasing as you go on increasing the number of robots. Wonderful picture. And the robots are completely reusable. The answer initially appeared to be yes, and people were absolutely excited about it, and it was a wonderful story. Now, as it happens in robotics currently, we've seen great videos with real robots, we've seen great videos with swarm robots, and both the communities, as in single robots and a swarm of them, both the communities are performing excellent. But then for our projects, as you would have known, having visited the robotics laboratory, if you ask me to believe on swarm robotics, then I do have my skepticism on that. So there are many tasks that there are many limitations that they actually cannot perform much of what as a customer or as a person who wants to get interesting jobs done from robotics from some robots, many things that they really cannot do. As in, I really need a cup of coffee right now. I'm not gonna research on how can a swarm of robots make it. I'm gonna invest money from government support and buy expensive robots, and then most of the limitations are gone. That means it's much easier to program them up and get my cup of coffee. So that's an interesting caveat that I leave you with. The other interesting thing that I leave you on exactly the same point is what are the limitations of what we've seen so far? Now, the limitations of what we've seen so far are that we have programmed robots, but I said that the work will keep on changing. So, can the robots program themselves? Natural swarms can. Nobody teaches ants, nobody teaches birds. So, can the robots together program themselves? And those programs will be better because it's just like, why don't we now do feature engineering in machine learning? Because it's based on human bias. My programs are based on my own bias, my own observations. Can the robots really learn themselves up? And if they can learn themselves up, it'll be a wonderful technology. Then I'll just have to buy robots and they'll program themselves. And their written programs will also be better because there are so many assumptions that I made about whether they can take the speeds that I give them or not, and whether they are budget robots, so the assembly is dented, the wheels are not straight, so can they identify and correct themselves in their own program or not? So we should be making self-learning robots that program themselves up, which is the wonderful field. And most of my efforts from now on will be eventually leading to exactly the same goal. Now, can this form of robots program itself? And today I leave you with the same optimistic note where I say that yes, we will make a swarm of robots that learn themselves so that you and me don't have to write down programs for them like we don't do for ants and birds. They'll be able to write their own programs. Which will be all for today. Thank you.